क्लास चालू है ना, शुरू हो गया, हो रहा है जल्दी सुना दो। Calendar dial, calendar dial, for dial, they are 26, 4s are 48, 5s are 60, dial 6 are 72, dial 7 are 834, dial 9s are 12 minutes, sorry, dial 8s are 196, dial 9s are 108.
So shall we start the lecture?
Yes, sir.
Okay then.
So in our previous class, we were discussing about the laws of reflection and refraction, and we just covered Snell's law. So Snell's law deals with, or it relates the angle between an incident ray and a refracted ray. So imagine that you have a material boundary, you have an interface between two materials with refractive index N1 and N2 with refractive index N1 greater than N2. So the medium with a larger refractive index is usually called as a denser medium, or to be more precise, you call it as optically denser medium. Optically denser medium. So optically denser medium means compared to the second medium, the first medium has a larger refractive index. And refractive index, if you recall, refractive index is defined as the velocity of light in vacuum divided by the velocity of light in that particular medium. So this value C by V, where C is 3 into 10 raised to 8 meter per second, divided by the velocity of light in particular medium. Let's say if it is glass or if it is silicon dioxide, usually the the velocity of light is of the order of 1.5 into 10 raised to 8 meter per second. So this value turns out to be, the refractive index turns out to be 2. So the refractive index is always a value which is greater than 1. The lowest value of refractive index that is possible is 1.0, which is for vacuum. So this is the refractive index of vacuum, 1.0. Air, even though it's a slightly denser medium, the refractive index is still close to 1. It's exactly something like 1.0000005 or something like that. So for all practical applications, we take the refractive index of air also to be 1. So the smallest value that is possible is 1. So larger the refractive index, slower will be the velocity of light, or slower will be the velocity of electromagnetic wave in that particular medium. Now you might have studied in your microwave course, there are certain artificially created materials whose refractive index is less than 1, or in other words, the refractive index is negative. So usually all natural materials have a positive refractive index, but you can artificially create certain materials whose refractive index has a negative value. It's not positive, rather it's negative. So those kind of materials are called as metamaterials. I don't know whether you have heard about this or not. It's called as They are called as metamaterials. So these are artificially created. These are created by humans. You don't find these kind of materials in nature, but artificially you can create these kind of materials where the refractive index turns out to be negative. So if you have a ray, and another thing is, usually when you write the refractive index, we write only a positive number. So you might expect that refractive index is always a positive one. Sorry, it's all. In fact, when you write a refractive index, you write only real quantities. So 2 is a real number. So you write only real quantities. But in practice, refractive index is a complex quantity. That means it's going to have a real part, so n real plus j into n imaginary. So there is always a real part and there is always an imaginary part. For almost all materials, the refractive index has a real part and an imaginary part. But for practical applications, we write only the real part. The imaginary part is, so the real part is the one which is associated with the phase change. Whereas the imaginary part, so if you write refractive index and if you see that the refractive index has an imaginary part, it means that the material is lossy in nature. So imaginary part corresponds to losses. So larger the imaginary part or the larger the imaginary quantity, greater will be the losses. Whereas the real part is associated with the phase change. The phase change. So whenever light propagates through a medium, it acquires some phase. So larger the real quantity, greater will be the phase that is acquired by the wave. Similarly, larger the imaginary quantity, greater will be the losses that will be associated with the wave propagation. So refractive index is an imaginary, refractive index is a complex quantity. It has a real part as well as it has an imaginary part. Another important point to remember is that refractive index is always wavelength dependent, or in other words, is always frequency dependent. Refractive index is never a constant. Refractive index is always frequency dependent or wavelength dependent. So that's also something which is very important to remember, some of the basics. Okay, so if you have a medium and let's say that the incident ray makes an angle of phi 1 with respect to normal, in all natural situations, what would happen is, you know that if N2 is a rarer medium, you know that according to laws of refraction, you would see that the refracted ray bends away from the normal. So you might have studied about the laws of refraction. So refracted ray bends away from the normal. So if the light is going from denser medium to rarer medium, the refracted ray always moves away from the normal. What about if it is going from rarer to denser? Then the refracted ray would be moving towards the normal. So you have studied this in your high school. So this is the normal situation where the refractive index is a positive quantity. If the refractive index is a negative quantity, then all these laws will not be applicable. Everything gets reversed. Okay, so what Snell says is that the incident ray, if it makes an angle of phi 1 and if the refracted ray makes an angle of phi 2, Snell's law suggests that n1 phi 1 should be always equal to n2 phi 2, where phi 1 is the angle between the incident ray and the normal, and phi 2 is the angle between the refracted ray and the normal. So all angles are usually expressed with respect to the normal line. Normal line is a line that is drawn perpendicular to the interface. And you also know that laws of reflection also says that the incident angle phi 1 and the reflected angle should be the same. That means this angle should be the same as this angle. So this law is what is called as the Snell's law. So the light propagation or the information propagation through optical fiber is actually based on Snell's law and total internal reflection. So we'll see what it is. All right. So let's assume that you have two medium. So you have a lower a medium with a lower refractive index. Let's assume that this is air, and you have a higher you have a denser medium. Let's say this is glass. You have an incident ray which makes an angle phi1, and then you have a exit ray or you have a refracted ray which makes an angle phi2. Now, if I start increasing the incident angle, if I increase the incident angle, so so if I make the angle like this, if I make the angle like this, then this ray would start going like this. So if I keep on increasing the incident angle, let's say that I increase this. So look at this figure, figure B. So if I keep on increasing the incident angle, you would see that at a certain angle called as the critical angle, which is defined as phi c, you would see that the exit ray would just graze the interface. It will be just passing along the interface. So this line, what you see, is the interface between these two materials of refractive indices N1 and N2. So if I keep on increasing the incident angle, you would see that the exit ray or the refracted ray uh, would just graze this. It would just go along the interface. So this angle, so the incident angle at which the exit ray or the refracted ray just passes along the material interface, so this angle is what you call as the critical angle. Is called as the critical angle. So at critical angle or at this angle, you would see that this angle becomes 90 degree. So critical angle is defined as that angle at which the exit ray passes along the interface, or in other words, it makes an angle of 90 degree with respect to normal. Now, if I further increase the angle of incidence, then you would see that, so if I further increase, you would see that this ray, instead of going along the interface, would be reflected back to the initial medium itself. So you are launching the light from this medium, it gets reflected in the same medium itself. So this phenomena, where you will not find any refracted ray, rather all the ray is getting reflected back. This phenomena is what you call as the total internal reflection. Total internal reflection, or in other words, you call it as TIR. So for TIR to happen, there is a certain angle beyond which there is a certain angle for the incident ray. If it is less than that, then the total internal reflection will not happen. The light would be exiting the medium. So this phenomena is what is called as the total internal reflection. So here now you had only one interface. You had N1 and N2. So you had only one interface. Now what happens if I put another interface over there? So this and if this let's say that I have a medium N2, then what would happen? So let's assume that N2 is less than N1. Then what would happen? This ray would continue passing. It would continue passing, and once it reaches the other interface, it would again get reflected back. So here you have the first total internal reflection. Here you had the second total internal reflection. So if I extend this medium towards infinity, then you would see that this ray would keep on bouncing between these two interfaces. So yeah, so if you have a ray like this, it would keep on bouncing like this. It will make multiple reflections. And then therefore by this process, it will travel from one location to another. So you place your transmitter here, you place your receiver there, and let's say that this medium is optical fiber, so you can send information or you can send light signals from transmitter to receiver. So this is how it happens in the case of an optical communication system. So so this figure, I took it from Wikipedia. So anyway, this just explains or this just represents what I have just explained so far. So if you have a normal ray, so let's say that this is a light source. If you have a normal ray, then you would see that a part of the ray is getting reflected, but most of them would be getting transmitted. So this is what is called as the normal reflection. It's called as normal. There is no bending there. There is no bending because it is 90 degree. So if the light ray is coming at 90 degree, then there is no bending. 90 degree with respect to the interface. But once I start increasing this angle, if I start increasing this angle, you would see that there is some reflection, there is also refraction. So I keep on increasing the angle. So at a certain angle called as the critical angle, theta c, you would see that there is a the light ray is flowing at the interface, and beyond that angle you would see that it gets reflected back. All right, any questions?
Sir,
Yeah.
sir, in the previous slide,
Yeah, go on. In the previous slide,
sir, for the third case, the intensity of reflected ray will be greater than A and B case, right?
what is that? Intensity of
Reflected ray in C case will be greater than that of A and B.
the intensity. Okay, so you are talking about this ray, right?
Yes, sir.
Yeah, of course, that would be greater because there is no leakage. So if you talk in terms of number of photons, so let's say that you are having 100 photons coming. So let's say that probably I don't know. It depends on so the number of photons that can escape actually depends on the refractive index difference between N1 and N2. So let's say that 30 photons escape and probably 70 comes in. And if you keep on increasing that angle, you would see that, so if this is 100, almost everything would be getting reflected back. So in this case, this intensity would be almost the same as this intensity. In reality, you will see that this is slightly smaller because there will be always some losses. We will study about that. But the reflected ray, the intensity would be almost the same as this ray itself. Is that clear now?
Yes.
Okay, fine.
Sir,
Yeah. So yeah, go
sir,
on.
you told that in metamaterials there will be negative refractive index. What does it signify? Like, how will be the refracted ray looking in that case?
Okay, so the metamaterial discussion of metamaterial is something beyond the scope of this course. So you would see that the light, yeah. So here you have, okay. So you can refer some review paper on metamaterials. Probably I think I have some papers, so I'll send it to you. But anyway, so if you have an incident ray, in normal cases, if the refractive index is positive, then you will be having a exit ray like this. The refracted ray would be like this. But if you have a negative refractive index material, probably the ray would be going in this way. So the loss, the direction and the angle, everything would be slightly different.
Okay, sir.
Okay, so this is, so you have these multiple so you have these multiple reflections, and you call these reflections as multiple total internal reflections. So multiple total internal reflection. So this forms the fundamental operating principle of an optical fiber. This is how the light gets carried from one place to another. Now in this process, you would see that the intensity at the receiver side, or the intensity of the photons, the number of photons that is reaching the receiver, would be always slightly smaller than the transmitter, what is being sent from the transmitter, because of various losses. So we'll study all those things in detail. But nevertheless, this total multiple total internal reflections is the fundamental operating principle of an optical fiber. Okay, so now let's closely look at an optical fiber. So an optical fiber is a dielectric waveguide. So it's a dielectric waveguide. So what's a waveguide? You might have studied about waveguides. So waveguides are those devices which acts as a channel for carrying electromagnetic waves or electromagnetic signals. So in the case of, for example, if you have a canal, now this canal is actually a channel for carrying water. Just like that, waveguides are the channels, or they are the canals for carrying electromagnetic waves. So if you look at how an optical fiber is constructed, so optical fiber is a dielectric waveguide, and it has a circular symmetry, it has a circular geometry. It's a coaxial cylinder, it's a coaxial dielectric cylinder. The center region is called as the core, which has a higher refractive index, and surrounded by that you have another material which has a slightly smaller refractive index, and you call it as the cladding. So core has a higher refractive index, cladding has a smaller refractive index. So that means N1 would be greater than N2. So this is the perspective view. So if I look at the side view looks like this. You have core and cladding. Cladding is having a smaller refractive index compared to core. So if I launch some signal inside the core, then assuming that it undergoes total internal reflection, satisfies the critical angle, then the light would be getting reflected like this, and it would be just flowing like that. Now, a realistic optical fiber, what you use for optical communication applications, does not have just a core and a cladding. It also have what you call as a buffer coating. So buffer coating is usually made out of polymer or rubber. So these coatings are usually used for increasing the mechanical strength. So this buffer coating is for increasing the mechanical strength and durability. So this core and cladding is usually made out of silicon dioxide, silica. Both of them are silicon dioxide. Silicon dioxide. And the power is predominantly carried by the core of the optical fiber. So core carries the information signal, and it carries it from transmitter to receiver. Cladding is actually a covering for the core, where it has a smaller refractive index, and covering the cladding you have a buffer coating which provides the mechanical strength. Okay, so you can have a cross section, you can have a look of the cross section of a realistic optical fiber. So you have the core and the cladding. So we'll be studying only about that. To study the property of optical fiber, we don't have to study the properties of coating and other things. We need to study only about the core and the cladding. So the center one is the core, carries the signal. Cladding has a smaller refractive. All these coating, strength member, outer jacket. So these are all mechanical. These are all the ones which give some additional mechanical stability. For example, outer jacket would ensure that external impurities or water vapor, water molecules, some dust, or those things does not penetrate inside. And then, okay, this gives some mechanical strength. Yeah, coating also gives a mechanical strength. Anyway, this is how a realistic optical fiber would look like. All right, so now let us see. So I said that whenever you are launching the signal inside an optical fiber, the angle has to be precise. The launching angle will have to be precise so that it can undergo total internal reflection. So if you don't properly launch the information signal, what would happen? If total internal reflection does not happen, total internal reflection means whatever signals, whatever light that is hitting this interface is entirely getting reflected back. That is what is called as total internal reflection. So in a good optical fiber that can be used for optical communication applications, total internal reflection is mandatory. All the photons that is striking at this interface should be getting reflected back to the same medium. And again, all the photons that are striking this interface should be getting reflected back, and this process should keep on happening. If this does not happen, then what would happen? some light, some photons would be escaping the core. If it escapes the core, then it ends up in cladding. That means you are losing some information signal. So ultimately, at every multiple reflections, if you are losing signal, then ultimately at the receiver side, you will not get any information signal. The demodulator will not be able to understand what you have sent it. So total internal reflection has to happen, and if that has to happen, you will have to properly adjust, or you will have to properly choose the launching angle, the angle at which you launch, the ray inside the optical fiber. So we can mathematically calculate what should be that angle. So consider a realistic optical fiber which has a core whose refractive index is N1 and a cladding whose refractive index is N2 and N2 is less than N1. So and this optical fiber is sitting in air. That means so surrounding this optical fiber you have air. So the refractive index is N. So you are launching the signal from air inside this optical fiber. So here is air. So this is air. All the other things are optical fibers. So let's see what should be the angle. What should be this angle phi that has to be properly chosen so that total internal reflection can happen. So this is an interface, right? So here is air and here is silicon dioxide. So this is the core of the optical fiber which has a refractive index of N1. So let's assume that you are launching the ray at an angle phi, and this makes so this gets refracted. It strikes this interface. Let us assume that this angle is theta 1. So you have a rectangle, you have a triangle here. This angle is theta 1. That means this angle should be 90 degree. This angle is 90 degree. So if this is theta 1, this is 90 degree, then this angle should be obviously 90 minus theta 1. And let us also assume that it strikes at an angle theta 1, it refracts, and the angle between the refracted ray and the normal is going to be theta 2. We are just choosing some angle and we want to find a proper relationship. Our aim is to ensure that no ray escapes the cladding. That means everything strikes back. So that's our aim. So when you are launching, you are going to see that you are having the first interface. So this is the first interface. So along this line, you have the first interface, and along this line, you have the second interface. So you can apply Snell's law at the first interface as well as the second interface. If I apply Snell's law at the first interface, what do I get? I get n into sine phi should be equal to n1 into sine of 90 minus theta 1. 90 minus theta 1, which is nothing but n1 into cos theta 1. So you get this relationship at the first interface. At the second interface, if you apply Snell's law, what do you get? N1 into sine theta 1. So I'm writing the Snell's law for this ray and this ray. This is the incident ray. This is the reflected ray, or this is the refracted ray. Similarly, for the first interface, this is the incident ray. This is the refracted ray. So at the interface 2, if I write Snell's law, I can write n1 into sine theta 1 should be equal to n2 into sine theta 2. Any questions? So n1
No,
into
sir.
sine okay, so n1 into sine theta 1 is equal to n2 into sine theta 2. Our aim is to calculate phi, to calculate this angle, the launching angle. So it's also called as entrance angle. So launching angle of the entrance angle, to ensure that total internal reflection always happens. or multiple total internal reflections happen. So, so from this equation, I can write an expression for theta 1. So I can calculate what is theta 1 from this expression. So what is theta 1 from this equation? So I get theta 1 is equal to n2 by n1 sine theta 2. So sine theta 1 should be equal to n2 by n1 into sine theta 2. So therefore theta 1 becomes sine inverse n2 by n1 into sine theta 2. So I get an expression for theta 1. And I can put this equation, I can substitute theta 1 in this equation. Therefore, I am going to get n into sine phi is equal to n1 cos of sine inverse n2 by n1 into sine theta 2. I'm just using some simple trigonometry. That's all. And if you use this relationship, let's say cos theta is equal to root of 1 minus sine square theta. If you use this relationship, then you are going to get so phi is going to be sine inverse n1 into root of 1 minus n1 by n2 into sine theta 2 the whole square divided by n. So you just have to apply this identity.
Sir, isn't it N2 by N1?
Okay, yeah. So this is n2 by n1, not n1 by, yeah, sorry, I made a mistake. So this is n2 by, yeah, this is n2 by n1. So that is n2 by n1. Yeah, so please correct that. So now, so we are trying to find, so now we have got a relationship between phi, that is a launching angle, theta 1 and theta 2. Now, if you want to have total internal reflection, then what should be the value of theta 2? What should be theta 2 for no ray to enter the cladding? What should be the minimum value of theta 2?
90 degrees.
The theta 2 should be pi by 2 or 90 degree. So apply that condition. So if theta 2 becomes 90 degree, then this expression becomes phi. So phi would become sine inverse. So sine inverse, what would you get? Root of n1 square minus n2 square. So n1 square minus n2 square divided by n. So you would be getting this relationship. Phi becomes sine inverse root of n1 square minus n2 square divided by n, where n1 is the core refractive index, n2 is the cladding refractive index, and n is the refractive index of the medium or the ambient medium. So in this case, n is 1. So if it is air, then n becomes 1. So then phi becomes sine inverse root of n1 minus the square root of n1 square minus n2 square. Now the physical significance or the physical importance of this value phi is that any ray of light which enters the fiber core at an angle less than phi would undergo total internal reflection. That means if the incident angle, so if I am launching an angle, let's say that my incident angle is less than phi. If it is less than phi, then it's going to undergo total internal reflection. If the incident angle is greater than phi, is greater than the launching angle, then at the interface, total internal reflection will not happen. So phi is defined as, so that is the maximum angle up to which you can launch a ray inside the optical fiber so that total internal reflection happens. And therefore, this angle phi is called as, so it has multiple names. It's called as the entrance angle, it's called as a launching angle, or it's also called as the maximum acceptance angle. Maximum, it's also called as the maximum acceptance angle. So beyond that, total internal reflection will not happen. Let's say that, for example, you have an optical fiber, the maximum acceptance angle is, let's say, 30 degree. So that means with respect to the axis of the optical fiber, this is the axis of the optical fiber. With respect to the axis, you can launch light rays up to 30 degree. That means this angle, 30 degree. So anywhere from 0 to 30. So you up to 30 degree, if you launch, the ray would undergo total internal reflection. If it is above 30, let's say 31 or 32, anything beyond 30, total internal reflection will not happen. You will have some reflected ray, but you will also have refracted ray. That means after a few multiple internal reflections, the ray would die off. You will have nothing at the receiver. So this angle is called as the maximum acceptance angle. So please remember this word, maximum acceptance angle. So,
Sir,
yeah.
sir, when you are analyzing, we're taking only kind of a straight core and cladding, but there will be bends also, right? Hello, sir.
Yeah, so we are talking about a straight optical fiber. If you have a bend, then obviously the angles would be different.
Okay, so
So
how
all
do
these all these bends are also responsible for losses inside optical fiber. So so when I discussed about the third generation optical, when I discussed about the third or the fourth generation optical communication systems, when I said that the maximum speed was 5 gigabits per second, and the distance between the transmitter and the receiver was like 70 kilometer. So you are asking me why it is only 70 kilometer. So the reason why the reason why the distance between the transmitter and the receiver cannot be made very large, even though the optical fiber has a small loss, is because of the fact that whenever you lay optical fiber, you cannot always lay it as a perfect straight line. You can there will be always some bend, and all those bends are going to cause some losses. So we'll study about those bending losses in optical fiber. So the equation what we have derived right now assumes that the interface between the core and the cladding is a how to say, is a straight line. In fact, the reflection happens only at a point. So even if you have a bend, the reflection happens only at a point, not along a plane.
Sir,
Yeah.
so even if we consider a bend, if we consider the wavelength of the light, the bend may be very small, and it would be a linear line itself, a linear
Yeah. So
cladding
we'll
itself.
okay. So we will discuss about those things. We'll discuss all those things when we discuss about bending losses in optical fibers. Okay.
Okay.
So please hold on. All right. So any questions on this maximum acceptance angle? Anything to get clarified? Okay, then we'll move on. Okay, so this maximum acceptance angle is extremely important, and in fact, this maximum acceptance angle. So based on this maximum acceptance angle, um, just give me a second. So we can define a parameter which is called as the numerical aperture of an optical fiber. So that's a very important parameter of an optical fiber. It's called as the numerical aperture of an optical fiber. So NA, what I have written here, is called as the numerical aperture. Numerical. So numerical aperture. So numerical aperture is defined as the sine of the maximum acceptance angle multiplied by the refractive index of the medium in which the optical fiber is situated. So the numerical aperture is given by square root of n1 square minus n2 square. So numerical aperture is a very important parameter of an optical fiber, and this numerical aperture physically means it defines the ability of an optical fiber to collect light. So numerical aperture can be defined for optical fiber. It can also be defined for a lens. For example, those who are very interested in photography, those who have worked with cameras would understand that a camera aperture has what you call as a numerical aperture. So if you want to take very good photographs, your camera should be able to capture as much light as possible, for which the numerical aperture of the camera should be as large as possible. So a camera is going to have a lens. So optical engineers, when they design cameras, they design the lens in such a way that the lens can capture as much light as possible. So that ability of a lens or that ability of an optical fiber is what is called as the numerical aperture, which defines the ability of the optical fiber to collect light. So the higher the numerical aperture, better is the optical fiber for collecting light. And that ability is that parameter is given by square root of n1 square minus n2 square. That means n1 is the core refractive index and n2 is the cladding refractive index. Now, how can you maximize numerical aperture? If I want to maximize numerical aperture, what should I do?
Increase the difference between
Yeah, so how is that possible? How can you increase the numerical aperture?
Take such materials. Which take such materials which have like the cladding is very low refractive index and core is very high.
use only the
Yeah.
core, sir.
So what is the material which has the least refractive index?
Vacuum.
Yeah, vacuum or air. So if you want to increase the numerical aperture of an optical fiber, the best way is to ensure that it has only core and no cladding. Cladding is just air. Then the optical fiber will have the largest numerical aperture. Though it sounds fancy in theory, practically it's not possible because you always need to have a material there. Otherwise, there will be a lot of losses and there are other practical difficulties. So we always end up with we always end up with a cladding material which has a slightly smaller refractive index than the core. But theoretically speaking, if you have an optical fiber with only core, that too with the largest refractive index, then the optical fiber is going to have the largest numerical aperture. All right, so so numerical aperture is defined as the square root of n1 square minus n2 square. There is also another important parameter which is defined as delta. This capital delta is given as n1 minus n2 by n1, where n1 is the core refractive index and n2 is the cladding refractive index. So this term, this capital delta, is called as the core cladding index difference parameter. So it's called as the core cladding index. Index refers to refractive index. So core cladding index difference parameter. Core cladding index difference parameter. So if delta is defined as n1 minus n2 by n1, and if numerical aperture is defined as root of n1 square minus n2 square, then use some simple algebra, and then you can show that the numerical aperture, so the numerical aperture can be approximated as n1 into root of 2 delta. So this you can easily show this. So numerical aperture is approximately equal to n1 into root of 2 delta. And for practical optical fibers, the numerical aperture is always between 0.14 and 0.5. So optical fibers usually have this numerical aperture. So again, since refractive index is a dimensionless quantity, numerical aperture is also a dimensionless quantity. Any questions?
Sir, why don't you make the cladding out of metamaterials?
That is practically very difficult. So what is the benefit you gain out of that?
Numerical aperture will increase.
How?
Since the refractive index will,
Even if n2 is negative, n2 square, you are taking the square, right? So how does it increase?
sir, I mean take something which is less than 1, like AR is n2 equal to 1, so less than 1.
Yeah, those things are not practically possible. Theoretically it's fine, but practically it may not be possible. You're talking about structures which are like thousands of kilometers long, and to coat those kind of metamaterials on the cladding, sorry, on the core is not, it's not practically, it's not possible.
Okay,
Well,
sir.
that's a good attempt, but uh, practically it may not be possible. And even metamaterials at optical, I mean, people have hardly demonstrated metamaterials at optical frequencies. They might have demonstrated them at microwave frequencies or maybe at acoustic frequencies, but not at optical frequencies. It's very difficult.
Okay, sir.
Okay, anything else related to numerical aperture or optical fibers or the core cladding index difference parameter? Okay, if nothing, then we'll move on to the next topic. So if this is the outside boundary of an optical fiber, and if I draw the axis, of an optical fiber, you would see that there is an angle. So this angle is what you defined as. So this angle was what you defined as phi. So that is the maximum acceptance angle. So if you have a straight line, and then if you have a ray like this, then you can actually rotate this, and then you can assume that you have a cone over there. So any ray which falls within this cone would undergo total internal reflection, and any ray which falls outside this cone would not undergo total internal reflection. This would escape. Escape means this will not reach the receiver. That means you are losing information signal. What we want is, we want everything to fall within this cone so that it undergoes multiple reflections and reaches the receiver. So this cone is also called as the cone of acceptance, or the acceptance cone. The acceptance cone. So launching the ray inside the optical fiber, you should ensure that it always falls within this acceptance cone, so that it undergoes total internal reflection. Okay, so I'll stop here. We'll continue in the next class. Any questions? Okay, if no questions, we'll stop here. Thank you.
Thank you, sir.
Yes, sir.